Okay, shall I start?
Yes, please. Good to go.
Well, good morning, everybody. Well, afternoon and evening, wherever you are in the globe. So I'm Keith Julian from the University of Colorado at Boulder, and I'd like to welcome you to the Physical Review Fluids Journal Club. Before starting the presentation by Geoff Spedding and Chanyi Oh, can I ask you to please mute your microphones, and also perhaps turn your cameras off to aid with the bandwidth. Okay, so today we have Geoff Spedding and Chris O from the University of Southern California. They will be making the presentation. Just a short bio. Professor Spedding received his PhD from Bristol University in the UK. That was followed by, or is followed by, a long and industrious career at the USC, including a bout as chair from 2010 to 17. He is an ASP fellow elected in 2010. And Professor Spedding has a broad areas of interest. And he's made significant contributions in particular, three areas in particular, according to his bio. He's made significant contributions to geophysical fluid dynamics, in particular the evolution of turbulence in oceans and atmospheres, including wakes from islands, which is the topic of today's talk. He's also made contributions to the area of image and data analysis involving PIV techniques and wavelets. And I guess he also dabbles in the details and mechanics of small flying devices, mechanical, and also birds and bats. Okay, so today's presentation will be of a paper submitted to the Physical Review Fluids in February, so it's relatively fresh, and it's on wave identification of stratified flows using dynamic mode decomposition. And this was in collaboration with his colleague, his graduate student colleague, Chanyi or Chris O. So Chris and Geoff, can I ask you to take it away? So I should say that questions should be asked in the chat function and will be answered at the end of the talk. And there'll also be a live session at the end of the presentation as well. So thank you. Geoff, can you take it away?
Hello, everyone. Thank you for tuning in. This is Geoff Spedding and this is Chris O. We'll be doing a double act today, so it's twice as likely that we'll go over time. And I'm going to give the introductory material, and Chris is going to talk about the nuts and bolts of this work, because after all, she did it all. She is a graduate student who is on the verge of graduation this year. So the paper is about an attempt to automate the identification of coherent structures in geophysical flows using dynamic modes, pictured here. The general topic of identification of coherent structures in stratified flows came about with us realizing that these structures are unusually persistent under certain conditions, actually under a broad range of conditions. There are two dimensionless numbers that govern the flow here, the usual Reynolds number, and a Froude number, which measures buoyancy timescales to convective timescales over an object of size L moving at speed u, in a stratification whose natural frequency of oscillation is the Brunt-Väisälä frequency n. Here is a set of a time series in dimensionless times from left to right, and different Froude numbers from 10 to 80. As the Froude number increases, stratification becomes less and less important. And the important point here is even when the stratification is weak, such as on this bottom row here, eventually, initially turbulent motion appears to evolve so that the wake is composed of an ordered series of coherent structures. There are a number of interesting questions. Where does this order come from? And can we detect it? And that's a rather wide-ranging topic here that each one of these pictures could take a talk in itself. But the interest here I want to point out is from millimeter scales to kilometer scales. Thousands of kilometer scales, so about 9 orders of magnitude of interest here. And geophysical fluid dynamics is in mesoscales is concerned with the dominant influence of stratification at some point in the evolution of originally disorganized material. Here are chlorophyll off the southwest coast of Ireland, and the transport of materials and nutrients is clearly affected by the presence of these coherent structures. And so we're interested in how that process works. And there's another constituency that is interested in this, and that's the Navy, our navies of the world, which for operational reasons are obliged to drive their boats through the ocean thermocline. And the evolution of these structures in the presence of these density gradients is hugely different than if the gradients were not there. The overall problem then is to look at a velocity field in the wake of an object which evolves in space and in time, and try to characterize it and understand where these characteristics come from, how general they are. Some old work showed that if you take a measure of the dimensionless wake spacing, for example, even at a range of Froude numbers of a couple of orders of magnitude, all wakes scale in the same way and decay with the 2/3 power of time. Yeah. It was also realized later on with Patrice Meunier that in fact by a suitable rescaling through an effective length scale, which takes into account the magnitude of the momentum flux into the wake, then all wakes from all types of bodies look the same too. And this was true of sharp-edged disks, of cubes, of streamlined bodies, anything. Well, therefore, we conclude that there is no memory of the initial conditions of a body in a stratified fluid. They all look the same. And one possible objection to this rather simple conclusion might be, well, maybe we haven't looked hard enough. Maybe we need to look in more detail at something more than just one length scale. And so early work using DMD to investigate vortex and wave length scales and separate them out in a stratified flow suggested that that might be a successful technique to then use that as a basis for automated pattern classification. And we did that in a series of experiments in the tow tank here and in numerical simulations, which were done together, covering exactly the same parameter space. This shows the streamwise velocity field in a frame of reference that is moving with the structures in the wake, and that comes from PIV data from this tow tank here. On the right is a crude description of the mesh that we used in this charmingly titled buoyant Boussinesque pimple foam solver. The upshot of this is that in Reynolds number, Froude number space, we've covered all of these dots here equally in experiments and in computations, and then made a classification of the patterns of the flow that we observe. This has been done before. Here's an effort by Chomaz et al., and here's an effort by Lin et al., and they're shown in dark and light colors respectively. And our classification is somewhat more simple, dividing all possible flows in this Reynolds number, Froude number regime into one of 5 possible categories. And the reason for that was, first of all, this is what we see. Second of all, it's more or less compatible with existing pattern classifications in the literature. And third, these are the patterns that emerge out into the near and far wake. And so we might be interested as a detector in trying to find out what those patterns are automatically. And so Chris will now describe what we did.
So as shown in the previous slide, all these 5 distinctive features can be used using the DMD-based as an automated pattern classifier. So DMD is a method to organize a flow field in the based on in the order of dynamical significance. So first, we take the flow field and then organize the data matrix into a column vector of each snapshot. And from this K matrix that contains a time series, DMD is performed on it, and we get a eigenvalue and eigenvector. These numerous modes then are based on the energy and the Strohal number threshold. Then we can find a dominant mode here that best describes the flow. So after getting the dominant mode, then with the known information about stratification, the physics of the stratified flow, we can go through this flow chart to identify what, based on looking at the flow matrix, what the classify into the 5 regimes. So first, the data getting the dominant mode, it first looks for whether the flow is non-oscillatory or oscillatory. So when there are no oscillatory modes that is filtered out from the energy and Strohal number threshold, then it moves on to the non-oscillatory branch. It first looks for the energy symmetry about the lateral direction to distinguish whether it's symmetric or asymmetric non-oscillatory regime. In the oscillatory branch on the right side, it first looks for the vertical symmetry of the dominant mode. And then within the planar motion, it looks for the lateral symmetry of vortex rate and planar oscillation. So, so just based on looking at a set of binary choices that are related to the physics of the stratification, we can identify these the flow into these, categorize it into these 5 regimes with the simple binary choices.
This would be a good time to say that these are your design choices.
Yes,
So
this is custom designed by me. So this can be used as an initial test for to classify the flow. So testing this classifier, so we have a 3D simulation and having the all available 3D data where 100% is 10 samples, 10 different time series. And you can see here that most of the cases were showing 100% accuracy, except for some of the cases showing lower accuracy, which we suspect that it's due to being in the boundary of 2 different regimes. Oh. However, in the real world, 3D data of a full time series is not always available. So what if the flow data that you get is limited to 2D matrix? So limiting the spatial information of the of data into 2D orthogonal planes, while we test that out as well. And then the flowchart is, everything is similar to what shown for the earlier one, but except that the variable that are used are using the variable that are available to us. So with the limited 2D data, the performances are still high for the simulation, but now some of the boundary cases showing lower performance. However, the real challenge is how is the performance when there is a existence of noise? And as you can see here is that there are many 0% and performing, the accuracy is very low. But But the highlighted, the red region here is referring to the non-oscillatory regime, where any of the dominant feature like Lee wave are fixed to the sphere, the body reference frame that is not spatially oscillating when that DMD cannot detect it, the signal is not prominent. And also DMD is known to be sensitive to noise that also inaccurately classify into a different regime. Something to note here is that these bottom cases where it has a red mark on it are cases where the full field is not available. It's not giving an accurate, is not a good case to,
the field of view is smaller than a characteristic wavelength.
Yes, the field of view is smaller than the characteristic wavelength to have an unfair evaluation. So what to do with the noisy data? Since DMD is known to be sensitive to noise, and one of the reason in previous literature have mentioned is that when taking the data matrix K and also a time shifted data matrix KP, then linearly fitting this operator is biased towards KP. So TDMD, total least squares DMD, introduced by Hemati et al., augments these two matrix and then doing the same eigen decomposition. And that way, the K and KP are unbiased and have less effect on the more robust when the noise is present in the data. So we tested out this TDMD where the top row is DMD and the bottom is TDMD with the SVD truncation. And you can see that just based on looking at the dominant mode, the noise is significantly reduced. And also, this is the case where symmetric non-oscillating regime, where based on the energy and Schroll number threshold, there shouldn't be any oscillatory mode that are significant. But and using the TDMD, what the mode that is supposed to be filtered out also reduce the energy, getting closer to be below the energy threshold for it to be filtered out by the threshold. So TDMD definitely helps, and TDMD can be implemented into the classifier.
So this has been a set of exploratory experiments, if you like, numerical and laboratory, on the feasibility of using DMD modes to make an automated pattern classification. And as you can see from the previous slides, the success depends very much on whether the data are noisy or not and how complete they are. So the two-dimensional slice results were much less successful, or significantly less successful, than the 3D ones. And we can claim, I think, moderate success on this example problem, which was deliberately chosen in the low Froude number, Reynolds number regime, where we know there are different and distinct patterns. And two sets of questions immediately come up here, which are these ones. Number one is, what else could we do? We just decided to choose the DMD classification because on a hunch, because it seemed like it might work. It does. But it doesn't necessarily mean it's the only method that works. And in particular, data-driven methods such as we've been working with Jonathan Tu at Carderock, and such as another adaptive method based on decomposition of existing data could work just as robustly. It seems to work. This paper has just appeared in PhysRev Fluids. this month. And the next big question, there are two big questions. Number one is, how robust is a method like this as the dimension of the input decreases? So as we go from 3D to 2D to maybe a series of 1D cuts, such as one might see in the field, what's going to work then? And can we be systematic about that? And the second thing is, suppose we expand to higher Froude number, higher Reynolds number regimes, where the flow is more turbulent, more disorganized. Will these pattern matching techniques work? We don't know, but we'd like to find out. Thank you for listening. This has been a joint production of Geoff Spedding and Chris O, and we're happy to answer questions.
Right, well, thank you, Geoff and Chris, for a very nice presentation. I see, I'll begin with looking at the chat. Yes, thank you. Yes, there's some appreciation being shown on the Hollywood squares. So one question in the chat, perhaps we can begin with that, then I'll probably ask that just raise your hands and
I think we lost Keith, is that correct?
I think I'm going to come back.
There you are, you're back, good.
I went unstable for a while. So let me begin with the one question in the chat, and then this goes to the earlier part of the presentation. Is there any reason these techniques will be invalid at slightly smaller scales, e.g. 1 to 1,000 microns?
I don't think there's any reason in principle that they wouldn't work, provided the flow is able to generate structure at those scales. So in fluid mechanical terms, we need to be above a Kolmogorov scale in order to see something dynamically significant, but there's nothing in the method itself that scales with scale.
Okay. I'm monitoring the chat. I don't see any hands up. Perhaps I can ask the question, actually. It goes to your regime diagram, and it's your really second point of low, this was sort of centralized around low Froude, high Reynolds. I guess you can perhaps speak some more about the technique at high Reynolds number and perhaps even lower Froude number, as well as the experimentation. What difficulties would you see in your, sort of extending experiments into those regimes as well? Just beyond the obvious that it's challenging. So.
Yes, the experiments that we run are in refractive index match fluids, and we use salt and alcohol as counterweighting fluids for modifying the density gradient without changing the refractive index. And we spend quite a lot of money on alcohol as it is, and things would start to become expensive and maybe perhaps a little bit unsafe if we tried to operate a bigger tank. And we need a bigger tank in order to extend the Reynolds number range out to the right here. To do that, I think the best chance of making progress in testing these techniques is through numerical simulations, which can easily run here and to 1 or 2 orders of magnitude to the right. It's fairly easy for us to go to low Froude numbers and even lower than this, and so extending this boundary to the bottom here will not be problematic. I think that the regime of interest to many is in the top right corner here at high Froude number and high Reynolds number. So what happens as we get out here? And here the flow is much more complicated. There are many more active scales because the flow is more turbulent, and we don't know yet, but we'd like to find out.
So would you see that the regime diagram will change in terms of this, your classification of flat 5 here as you go out in that direction?
Yeah, in the worst possible case, there'll just be one regime, which is turbulent mess, and we won't be able to say anything sensible about it. However, we don't know that yet, and it may be possible for, and the fluid mechanics literature suggests that it's not hopeless to look for coherent structures that can say something about the majority of the dynamics, even when the Reynolds number is high.
Okay, we have questions that are coming in on the chat now. So one from Nimesh: can DMD be used as a compressed sensing algorithm, Or in other words, can it be used to enhance the spatial resolution of coarse experimental data sets and reconstruct it with a finer resolution using information from the dominant modes obtained by DMD?
I think the short answer is yes, it could be used that way. And there are some people who are working along those lines. We haven't. There's a related question here. What could be the possible about what happens when the data are deliberately undersampled? And we haven't yet made systematic studies of that beyond what we showed you. And it would be interesting to see that, to find scales and measures of sparsity where the technique no longer works.
Okay, and
Chris, you have to answer the next one.
Okay, another question in the chat. I'm not seeing hands raised yet, so I'll stick with the chat. Really from Henshan, really interesting work. If the data is downsampled in time domain, will DMD be robust enough to handle it?
I think this kind of ties with how Dr. Spedding said. We haven't done a systematic study on how, if this data is sparse or like limited, but DMD definitely needs enough snapshots for DMD to converge, like similar to looking at FFT. Like it needs to have a full wavelength or the frequency cycle for it to detect if because it's looking for this coherency. So if I don't even have a full cycle, then it will not. It will more focus on smaller scale, like noise. So if you're downsampling very, very low, then it will not perform well. But we don't know what that limit is yet.
Okay, thank you. One question for Pavan. We're still getting down into the nitty-gritty of the DMD here. They're asking about the size of data matrices. What can you handle as a possibility, and how can we get to, or how we can get to know much data to collect for less error? I'm not sure if I'm portraying the question correctly. Perhaps Pavan can step in if I've said it wrong.
You want to try that?
So
there we go.
So so the size of, in terms of how large
your K matrix gets quite big, right?
So K matrix, because when I'm processing the data matrix, it's already it's a simulation with a high relatively high spatial resolution in 3D. So the data matrix itself is pretty high, and there are many ways to try to reduce the computing time, but then processing itself, I don't think, because you will just have a large matrix that you're doing looking for linear fitting, looking for the linear operator. So there's no limit as long as you have enough time and the computing power.
But I think also we've successfully used this streaming DMD where you don't recalculate the entire K matrix every time, but you just increment it as each time step goes on. And that, of course, is the success of that. The feasibility of that is absolutely essential to have this work for real data. And Chris has done that.
Right. So I can, the more data I have, the better accurate the performance of this classifier I would have. But it was more of, and also like with computing power, as Dr. Spedding mentioned, using the streaming DMD, because you're no longer stacking all the snapshots. You're updating the DMD modes whenever each snapshot is available and toss it out, or no longer needing the previous snapshot. But also that's helpful in a real world application where you need to lively update this. If I'm a if I'm detecting or trying to look for these weights that's moving lively, then I need to constantly update for a better accuracy as the information is coming to me. Yeah, and the streaming DMD, although it was not on this paper, when it was for the test case, it was showing pretty close to what was similar to DMD.
Okay, thank you. So we're getting to the bottom of the hour here. So last question, and from Bruce Sutherland, a Bruce Sutherland type question, I may add. Can DMD be used to separate wake flow from internal waves generated by the wake in circumstances in which this occurs?
Yes, hi Bruce, thanks for the question. The answer is yes, and the results of that appear in an experiments in fluids paper in 2017, and that's the first thing that occurred to us to do, is to separate the vortex and wave modes in a flow that we knew quite a lot about. And so, yes, I'm happy to say it. And also, if I may make a sort of general comment about a number of the questions, it's a very live or even lively topic about to what extent can we get away with reduction of the resolution of the data, either in space or in time. And we look forward to being able to do that systematically in the future.
Okay.
Thanks a lot, Geoff.
Well, thank you. Perhaps we can end by thanking Geoff and Chris for a wonderful presentation and on this relatively fresh paper published in PRF. So thank you so much. And I guess this will conclude the Physics Review Journal Club.
Well, thank you, editors, for publishing it.
Thank you.